Okay, so we are recording. As far as the software, I mentioned before that you're welcome to use SAS or R, either one. Somebody pointed out that, that there's a lot of questions that may be easier to do in SAS. Depending on your background with R, I'm thinking you can probably do a lot of the questions in R, like probably at least 70 to 80%. And that's fine. Like I'm not, I know I gave you a little bit of SAS code for the homework here, and it may be the easier way to go this time. I have had people do R for like homework 1 pretty easily. There's only, I would say there's a few, handful of questions that will probably be easier to do in SAS, but you can use R. You might have to kind of do it on your own, figure out what the code will be for that. But I know that more and more people are using R. Like 10 years ago, R was there and it was used, but not for, for the courses that we're teaching, not used as much. Definitely you guys are using R more than graduate students like 10 years ago for statistics. And I think that's good. I know that you have classes now that are really taught with R. So I'm sure a lot of you are good with it. I'm trying more and more to get R, equally represented in this course as SAS is, but it's still a little bit more towards SAS. Little by little, each year I'm trying to get R more into it. What are you going to use in the future? It really depends. Like if I didn't have an employer that purchased SAS for me, I doubt I would buy it on my own. I'd probably try to figure out how to do it in R. But you may have an employer that, will buy that. And, the biggest thing I want to stress though is that a lot of people or some people tend to feel like they want to do one thing. They want to have R as their software or SAS as their software and think it's great. There's limitations to just pigeonholing yourself into one software. I would say try to learn both and use both for their strengths, because each one has its strengths, each one has its weaknesses. But I think it's a pretty good idea to really learn both, at least a little bit. And then, like any language, you're going to have your first love, right, for what you go to, and that's understandable. But I would just encourage you to learn both, at least a little bit. Any other quick questions on homework or any logistical things?
Is that due at 5 or at midnight?
For 11:59.
Okay.
Well, I think I know on the homework it said 5, but automatically when I make it due on Canvas, unless I change it, it says 11:59. You can turn it in since I had that later time on there and I posted that yesterday, I'll leave it at that. We'll just we'll go with the 11:59. So if you need a little extra time this evening, you can finish it. But please get that in today sometime. Yeah.
Thank you.
Yeah. Anything else? All right. So last time we left off in the slide set 3, and just have a little bit to finish there before we go on to the new slide set. And so we're going to talk about, you have a mixed model. How do you estimate the parameters? And if you've had theory, you know that maximum likelihood estimation is a pretty common way to estimate parameters in a model. So what do you need in order to do maximum likelihood estimation? What do you need to know?
distribution.
Yes. Who said that? Jonathan. Okay, yeah, that's right. You need to know the distribution. And specifically in our case, when we're talking about mixed models, you need to know the distribution of the outcome, right? Because that's what you use to create the likelihood, right? It's based on the distribution, in particular, the probability density function, you know, for the outcome. And how do you, so you have a distribution, right? You have a distribution for one of the responses. How do you take care of all of the possible responses for a subject? If there, let's say there's multiple measures, what kind of distribution do you need to be concerned about in that case?
Do you have to get the joint?
That's right. You have to get the joint distribution. So we're talking about a multivariate normal. And the multivariate normal allows us to specify the covariance structure between the repeated measures. And that's this V, right? Again, I'm pressing extra buttons here. So that's where the repeated measures comes into play. We can account for the repeated measures through that V matrix, and that's what we talked about last time. That's this thing up here. Not sure where the V went. Let's see. Yeah, so that was, I did that proof, but that's this thing up here. That's our V, and that's how we account for the repeated measures. Okay. What about taking care of multiple subjects though? How do you account for multiple subjects in our likelihood function? What if we can assume that the subjects are independent of each other? Then how do we create that full likelihood that accounts for not only measures within a subject, but also the measures across different subjects?
Do you think covariance matrix can be helpful in this scenario?
It could be, but if the subjects are independent of each other,
Yeah.
then what does that allows us to do something, right? Because if they're independent of each other, then what's going to happen to the covariances between the responses between subjects?
Go to 0, correct?
Yes, exactly. There'll be 0, right? And what you can do then is actually multiply those densities. So you have a multivariate normal for an individual subject, and then you have a multivariate normal for another subject, and you can just multiply those across subjects. And that's the way I've expressed it on this page here is a product of multivariate normals for the n subjects that we have.
But Professor, covariance will be 0, then when we are multiplying with the subjects, then it will become 0, right?
Well, the covariances are 0, but the densities, you will have positive densities for each subject. And so you still have a positive likelihood. So yeah, that's a good question. So we have a likelihood that's based on probability density functions for subjects, and we multiply those across subjects. And then what do we do in order to estimate those parameters?
You take the derivative.
So a couple of people respond. So Jonathan, go ahead.
Do you take the derivative to find the maximum?
Yeah, so when you take, what happens when you take a derivative?
Do you set it equal to 0?
Yeah, so you're doing a little calculus, right? So that you, essentially you're maximizing that likelihood. And that's one way to do it. You can set it, you know, at least that's when you're working with the algebraic form, you know, you take the derivative, set it to 0, solve for the parameter values in terms of the data. And that tells you what the estimates will be. When you're dealing with the mixed model, you have to use a numerical method. It's, you know, it's not algebraic. You have to use a numerical method, but it's the same principle. You're maximizing the likelihood, or you're minimizing. The form that we usually use is -2 log likelihood, and you minimize that, but it's the same principle. Okay.
Hey, Matt,
Yeah.
what is that R in that equation at the beginning? The R total.
Oh, that's the total number of measures. So that's a good question. So R sub I is the number of measures for subject I, and the R tot is the sum of those across all the subjects. This form down here that I've written in terms of multiplying it across the subjects is probably the more useful one that you're actually gonna maximize. And there's a few other things in here. What is the, you know, where are these lines indicating? That's the determinant. So you have this matrix, and then you find the determinant of it, and then take that to the -½ power. So it's pretty complicated to actually carry this out, but that's what the computer does for us. Actually maximizes it, tells us what values of the parameters give us our estimates. So it's all done numerically when you have a mixed model. When you have a GLM, just a regular linear model, you can get an algebraic form, but probably still use a computer, right, to get a numerical answer for you. So one other thing I want to point out, this matrix V, like we talked about how, you know, we derived that. That's a combination of the covariance matrix for the random effects and the error covariance matrix. And there's different ways we can specify that. So we talked about last time how if you have a random intercept model, even if R is sigma squared I, then you've induced a compound symmetric correlation structure. Or an alternative way is to not have a random intercept and then specify the compound symmetric structure on R, and that gives you the same V. Okay, so there's different formulations that lead to the same model, and when you maximize the likelihood, we're just dealing with V. We're not dealing with G and R individually. So that shows us why you can fit the mixed model different ways. You can have a random intercept with a simple R structure, or you could have a compound symmetric R structure and no random intercept, and you get the same model fit. What's the benefit of doing one or the other? Well, obviously, if you do the random intercept, you have specific subject estimates. They're random effect estimates, and they're deviations from the average. Whereas you don't get that when you do the CS structure directly on R. But numerically, there may be times when one may work better than the other, okay? So I'm gonna jump over some of this, and I think you guys can just read some of this detail. When we do maximum likelihood estimation in a mixed model, I did mention we do that numerically. However, if you condition on the covariance parameters, you can get an algebraic form for your fixed effect estimates. And it looks a lot like what we see for a general linear model. It's just that you have an extra V inverse inside. So that's what the algebraic form looks like for the estimator of the fixed effects. And what we can do then is what is that a function of? It's a function of your covariance parameters that show up through V. So if we plug this formula back into our likelihood, then we actually have a new likelihood that's re-expressed in terms of the covariance parameters, and we can maximize that. And that's usually what's actually done. So that different formulation is called a profile likelihood, and that's what we actually maximize. And like when you run proc mixed or whatever software you're using, usually it's a Newton-Raphson type of algorithm that's used to actually maximize the likelihood. And you'll see that in a note when you run proc mixed. You'll see, you know, something like Newton-Raphson ridge regression or something like that. And let's see, what else have I mentioned here? So that MLE solution that I talked about, if you use the profile likelihood, it's the same as simultaneously estimating the covariance and fixed effect parameters, okay? So what we did is we took that likelihood, we conditioned on the covariance parameters in order to get a form of, an algebraic form for our fixed effects, and wrote our profile likelihood, and then maximize that. And then you can stick those estimates back into that formula we have for beta hat. But that approach that's normally taken is the same as if you just simultaneously maximize the likelihood with respect to our alpha and beta parameters. Okay, now what's the difference between maximum likelihood estimation and restricted maximum likelihood estimation, or REML? In a nutshell, I'm not going to spend a lot of time on this, but just to tell you basically what we do in that situation is we write a new likelihood that eliminates the fixed effect parameters. So it becomes a brand new likelihood called a restricted likelihood, and it's completely eliminating the fixed effect parameters in there. So it's different than the profile likelihood. Why do we do that? Why would we want to eliminate those? Because we will get less biased, unbiased, or at least less biased estimators of our covariance parameters. And an analogy or a simple case to think of that is, let's say you just have a random sample and you're drawing from a normal population with mean mu and variance sigma squared, right? What is, so if I have space to draw here, yeah, this will be good. So we're drawing from a normal population. So we have x1 to xn, normal, mean mu, variance sigma squared. What is the MLE of sigma squared? You guys, anybody from theory remember this one?
Is it the sample variant?
Not quite. It's close to that.
1 over n minus 1. Sample variance over n minus 1.
You're kind of close to it. You're on really close, very, very close. We have in the numerator, we're going to have this thing, right? What do we have in the denominator?
N minus 1.
No, not quite. That is the one that we use. That's the unbiased estimator when you have n over n minus 1.
Okay.
And that's the good one. That's the one that, you know, we like. That's going to give us an unbiased estimator. But if you actually derive the MLE in this case, you're going to actually have n in the denominator. That's the MLE, okay? So that shows you that the MLE is not necessarily unbiased, okay? So we know that if we take divide by n minus 1, that's our s squared, right? And we know that the expected value of s squared is equal to sigma squared. That's the one that we use. That's a sample variance, right? But the MLE, if you derive the MLE, you get your likelihood, you maximize it. And in this special case, we're just talking about a simple random sample. This is not a mixed model. You have n in the denominator. And that shows one of the downsides of the MLE. And that's the purpose of REML, is as you generalize, we're trying to take away that bias, okay? And that's how you can do it. So the way that you do that is by re-expressing the likelihood, not just re-expressing it, but rewriting the likelihood, eliminating the fixed effects. Okay, so again, with this simple example where we just have a random sample, the MLE of sigma squared is how it divides by n. But what if we had, what if we didn't have to worry about the mean, estimating the mean? I just want to talk about the difference between these two real quick. If we actually knew what the mean was, mu, then what would we use to estimate the variance? We could use n in this case, right? The reason why there's a difference, you can think about it this way. What happens when you draw a sample, and if we distinguish these two quantities, say we have x squared in this case, why do we put in x, or not x squared, x bar? Why do we put in x bar instead of using mu? It's because we don't know what it is, right? We don't know what that mean value is, and that's why we use x bar. But if you look at the difference between these quantities, what do you know about xi minus mu quantity squared versus xi minus x bar quantity squared? What's the difference between those quantities? Which one's going to be bigger? Just think about taking a random sample. Let's say you take 10 values, you take a random sample of 10 values. And yeah, go ahead. Somebody's going to talk.
The bottom one should be bigger, because if you haven't perfectly predicted the population mean, we know that like the population mean is the point that's closest to all the other points when the variance is minimized. And so if your sample mean is different than the population mean, your variance is automatically going to be larger. Because the squared distance from all the points to the means is smallest when you have the population mean. Maybe.
What did others think about that one?
I actually thought it would be different because your X bar is informed by all of your data. So it's more likely that your data points would fall closer to X bar. So then that squared quantity would be smaller.
Okay. What do you think about that, Matt?
I think that's a great idea.
I really liked your first answer. It sounded really good. But Samantha's actually right. You think about it this way. Mu is not going to change depending on the sample that you take, whereas X bar is going to tend to follow your data, right? So if you tend to have a smaller sample, smaller values for your sample, that sample mean is going to be pulled towards those smaller values. If you tend to have a larger set of values, that mean is going to be pulled up to it. So this quantity xi minus x bar squared is going to tend to be smaller than xi minus mu quantity squared. And because of that, if you think about it this way, then you need to divide by less in order to keep that whole thing the same. That's why we divide by a little bit less than we do in this case up here, you know, so that we can keep that whole ratio about the same. That's one way to think about it. Okay. Now REML is doing kind of the same thing. You're eliminating the fixed effect parameters from your likelihood, and then that's going to lead to unbiased or at least less biased covariance parameter estimates. The problem with REML is that you've eliminated the fixed effects altogether. So how do you estimate them? Because we are interested in them. And what you do, this is typically what's done, is they say, okay, well, we know we don't have any beta parameters in our model, so let's just go back and use that formula that we came up with before, you know. But the thing is, this is based on maximum likelihood estimation. So that's the one weird thing about REML, is that you don't really have a true estimator for the fixed effects. You're kind of using a hybrid approach here. You're making a new likelihood that just involves covariance parameters, getting good, you know, less biased estimates for those. But then you're saying, okay, let's just go back and use the ML form for the fixed effects parameters. So that's the point that I'm making here on the slide. So the common approach is, let's see. The common approach to estimate beta is to plug in REML estimators of our covariance parameters back into that first equation. But that equation was derived using ML methods. So this estimation of beta is really based on a hybrid of ML and REML methods. Okay, and for that reason, a lot of statisticians just like to use ML, maximum likelihood estimation. I personally, I don't have that big of a problem with it. I'll go with REML because I feel like, in general, because, you know, it works, right? It's maybe not as clean theoretically, but the point is we're trying to get better estimators of our covariance parameters that are not going to be artificially inflated. So I tend to go with it. It's actually the default. Like if you use SAS proc mix, by default it's going to use REML, and I believe R is the same with the packages that use in R, that REML is going to be the default. And you have to say specifically method equals ML if you're going to use maximum likelihood estimation. All right, so that's that. Any questions on that? If not, we're going to jump into the next slide set. And this is review. So this week and next week is what I call review. You know, some of it may be new, or maybe you forgot, so maybe it looks new. But I think, you know, after many years, I feel like I really want you guys, instead of racing through and then you don't really have a good foundation, I probably mentioned this already. I really like you to have a decent foundation, and then we can kind of go faster through some, you know, more advanced material later. The mixed models, we won't race through that, but there are some topics towards the end that I'm just going to be able to kind of give you the idea for those. So today we're going to talk about the linear mixed model random intercept model and how that relates to repeated measures ANOVA. Can anybody tell me what is repeated measures ANOVA? And I said this, you probably read it. It doesn't bother me if you're, honestly, it really doesn't bother me if you're right or wrong in your answers. It's effort is really the biggest thing. So don't be like, oh, I don't want to mess up. I'm not too concerned about that. If you give me a decent try, that's the important thing. So did you talk about in 6612 repeated measures ANOVA, and do you remember? There's I see an orange button here in chat. Some questions or something?
Sorry, I just tapped to the wrong person. Sorry.
Oh, okay, no problem. All right, so the repeated measures ANOVA. You remember that term? You still see it, you still hear it a lot, like in grants and papers. Oh, we use repeated measures ANOVA.
Is it like the correlated sample we have and we are going to find the ANOVA? As in the finding variance of correlated sample, and that's why it is repeated. So
yeah, so that's right. You have your ANOVA. Or when do we use ANOVA? It's when you want to our analysis of variance. I guess that's good to start there, just a step before. Okay, you guys should know this one. Analysis of variance, right? What do you use an analysis of variance for? Is it to compare variances between groups?
Compare means between groups.
Exactly. It's kind of a weird name, right? Analysis of variance, but we actually use that when we want to compare means between groups, right? But the ANOVA table is what one of the first things we learn in linear models, and it's a nice intuitive analytic approach because you're taking the total variability in the data and you're breaking it down into different pieces. But then you build test statistics to compare means between groups with that. And the repeated measures of ANOVA is basically using the same approach. You have that ANOVA table, but you then make an adjustment to account for the fact that you have repeated measures. Okay. So we talked about this last time. You know, we had our random intercept model, and we showed what the covariance matrix would look like for it. So the variance is going to be sigma b squared plus sigma epsilon squared, and then the off diagonal is going to be sigma b squared. And if you do the correlation version of it, the off diagonals are actually going to be sigma b squared over sigma b squared plus sigma epsilon squared, and that's actually the interclass correlation coefficient, right? So the random intercept model yields some pretty intuitive quantities of interest. So turn this off. Okay. So I'm going to just present some fitness data. So 10 subjects were randomized to 1 of 2 fitness programs. One was a lower intensity and one was a higher intensity. And they were given a overall composite fitness score that could run from 0 to 75. And there's enough possibility in the responses that we can model that with the mixed model. And we have repeated measures. So we have week 0 as the baseline. And then as they start their program, we're going to see what that fitness score is going to do for these subjects. And then ultimately we want to compare between the 2 programs, the higher intensity versus lower intensity programs. So here's the data. And we see that the fitness scores tend to increase over time. So we have the 5 repeated measures, and we have, you know, to keep things simple here, we have complete data. And what are some things I'm gonna keep asking questions. What do you notice in the data? What are the things that kind of are striking about the patterns in the data?
One thing I notice is the baseline matters a lot. So people who started higher are going to still be higher than people who started lower.
That's a good point. Yeah, so a little bit like the REML data, where if you start off more fit, that it seems like you stay at a higher level, and the people that are lower, at least within this time frame, they're not going to pass people that were fit. At least, you know, by the end time point, right? So that shows us, what does that show us? That one of the key, in terms of variability, what source of variability are we talking about there? What you just said, Elise, I think to me that indicates between subject variability, right? Or just the, you can think of it different ways, like there's just an intercept difference between the subjects, right? Or a mean difference. I mean, you can think of it either way, whether you compare it at the zero value or over here or at the mean value. There's just an average difference or an intercept difference between the subjects. Anything else that you guys see?
So the orange groups are more similar to one another than the green group.
Yeah, definitely see that. So you can see less variability in the orange group. So that's the lower intensity program. That's a good one. Anything else?
It looks like the slopes for the green group tend to be steeper.
Yes, especially in the second half, right? Because you notice, like, initially they're not climbing that fast, but after a couple weeks, like it looks like it takes a while. Like, you know, the intensity of the program may be pretty tough to see an initial gain, and maybe they get really sore or whatever. But then after 2 or 3 weeks, this higher intensity program seems to have a stronger effect, you know, especially in the second half of this study. So the green slopes higher. Importantly, I think you see what you probably would hope or expect, that both programs are impactful. One may be more impactful than the other, but everyone's increasing. So what effect would that, what source would that, would I be talking about there?
Do you mean like a treatment effect or a group effect?
Yeah.
Like within subject?
Yeah, I think that's correct. Within subject, but also, like, if you, let's say we have group by time, subject in our ANOVA table, right? Those are the 4 that we're going to focus on. The one where you just tend to see an increase as you go along.
It feels like the interaction term between the group and the time.
Yeah, there is an interaction for sure, group by time. So that's saying that that the patterns over time differ between the 2 groups, right? You see the higher rate of increase for the green one. But going back to my original question is, you tend to see both groups going up, right? And so that would be the time effect. That, you know, just in general, if you average over the groups, everyone's improving. You know, the fitness programs are both helping. But Randy, you're right that I see an interaction there. So we would expect, you know, there's a time effect. There's a group by time. Is there a group effect? What would the group effect be? And it's important to distinguish a group effect versus group by time. How do we figure out the group effect here?
The intercept.
Go ahead, Randy, say it again.
It should be the intercept between the two different groups.
One more time, sorry, a car was driving by and distracted my audio.
It should be the difference between the intercept of those two groups.
Yeah, so really though, I think it would be the mean. So you just, the same principle, just shift over. Think of averaging over time in this case and comparing the groups once you've averaged over time.
Wouldn't you have to flip the groups? So the individuals in the high intensity, put those in the low intensity, and then move the low intensity into high to remove the effective time?
Flip the groups. I guess I'm not quite sure.
So that your individuals are now in two groups, and then after the 4 weeks, you switch the individuals into different groups.
And then, a crossover?
And then you can move the effective time.
That would be the best way to do it, yeah. Yeah, that's a good comment, right? But in terms of actually, for the data that we have here, if we want to figure out the group effect, you can think of just averaging over time and then comparing the two groups. So for example, like we take the subject, just average those 5 values, average those 5, and so forth. And then you compare the means between those two. To me, it doesn't seem as clear. I mean, there might still be a difference, but it doesn't seem as clear as the time effect and the group by time effect. To me, visually, those are the most striking. So we'll actually look at the numbers here and see if it matches what we. So you guys mentioned a lot of the important features that we see, and I think that this is one thing I want to stress too. Like we're learning some pretty advanced methods in this course, but the results that you get should match what you see. If they don't, then look at what you did more carefully, right? We have fancy ways of estimating things and getting standard errors and so forth, but the results should make sense. So that's the thing, like when you're doing your project, you apply your methods, get your results, great, but do they make sense? I mean, don't forget those simple things to look at. So, why are we talking about repeated measures ANOVA even though we have mixed models which can do the same and more? Well, I like the idea. I like the idea of repeated measures ANOVA because, and to show that it's equivalent to one type of mixed model when you have a random intercept model, because it's a very intuitive way to look at the data. We have a bunch of variation and we're partitioning it into different pieces. And so I think it's very intuitive. ANOVA tables are very intuitive, even though inference in mixed models is generally not done that way. In some special cases, it will be the same. So in general, inference in linear mixed models are not based on ANOVA tables, but in some cases, it's the same. So our model, are you guys comfortable with writing models like this, like statistical models? It's kind of important to be able to write out a model and know what the parameters are that you're estimating in the model. So this is one way to write a model in this case, where we have group In this case, we only have 2 groups. So H could be 1 or 2, right? We have our 5 time points, and the effects then that we're expressing here are, these are both class variables. In other words, we're allowing estimates to be flexible here. We're not forcing a straight line through the points. And it's kind of important, right, that we're allowing that, because it's hard to say that there's linear. Like for one group, it looks like it could be linear. There's a pretty steady pattern, but we're allowing flexible estimates here. And when we treat group and time as class variables, then we get the most flexible fit. And then we can go back and say, okay, we can simplify this to a quadratic or a linear if we want. But in this case, we're just treating them both as class variables. And we have an interaction between group and time, again, making it the most flexible model as possible. My indicators, we have H is going to indicate the group. So that's 1 or 2, or it goes, it goes up to 2. I is going to be subject, and J is going to denote time. So this is typically what I do. A lot of longitudinal models, I'll have Y, I, J, subject and time, but sometimes it also helps to add H to indicate if you have a group. So you'll see this pretty commonly done. You could call this interactive effect something else, but here I use gamma and tau together, and it kind of emphasizes the fact that it's an interaction effect. And then I have subject within group. So that's you see this convention used in SAS. So this is, you can think of this as subject within group. And that's sort of a borrowed notation that SAS typically does. And then we have our error term. So our subject within group is this one. So that's our model. And those are the parameters that we're interested in estimating, the gammas and the taus and the interactive effects. And then we'll have a variance associated with this term for subjects within group, and variance for that error. So what's the difference between just subjects, variance of subjects overall, and subjects within group? Well, if you can think of a mean effect for group, let's say it's gonna be messing with me again. Let's say that we have our lower intensity mean there and our higher intensity mean here. And we have subjects in our lower intensity group are going to be about that point, and subjects in our higher intensity group are going to be around this point here. So if you consider the variability of the X's and the O's all together, just the variance of those, regardless of what group they're in, that's the variance of the subjects. But if we're looking at, if you're just focusing within a program, the variance of the subjects within programs, then that would be the subject within group variance. Okay, so you're eliminating differences between the two programs and focusing on the variability of subjects within programs. Okay, so our ANOVA table, we have group, and I kind of simplified, so this would be group. This is time, then we have our group by time and subject within group, and then everything else is residual. So those variabilities add up to the total variability in our data, right? Where we just take a value and how different is it from the overall mean? You square that, and then you do that for all the values that you have in your data. That's the total variability. And we've broken that down into different sources of variability. And from this, we can run our tests, right? We get our mean square value for each source, and we divide it by the residual mean square. And what kind of distribution would that quantity have? Mean square for a source divided by mean square for error or residual. You guys remember that one?
F.
Yes. Okay, 2 of you got it. F distribution, right? Where you have a ratio of variance quantities, and that has an F distribution. So the other thing we can do, which is going to help us, is we figure out the expected mean square. So this mean square quantity, you know, if you go back to the sum of squares, we have our y's involved, and we know the distribution for those. So we can figure out, you know, the distribution of that quantity. And I actually did this in class. I used to do this. It's kind of messy. It's just, but it's mainly algebra and theory and so forth. And you can derive the expected mean squares just using theory. And this is given on the right-hand side. And that's going to be helpful here in a second, and I'll show you why. Okay, but again, we have a nice table where we have the total variability, broken it down into sources. Makes sense, it's intuitive. So how do we use that? Well, we can do our, use our F tests for our different sources. And you notice here that for tests involving group by time, for subject, and for time, we use the mean square residual in the denominator, whereas for group, I'm not using that. I'm using a different denominator. Okay. Now, by default, if you were to run this in software and you don't mention anything about the repeated measures, this quantity here would be mean square error, mean square residual, right? If you didn't tell it anything else. And that, what we're going to see is that that's going to lead to results that are a lot different. And I make a note here that, you know, as far as that variance term for subjects within group, you can do a test for the variance, is the variance 0 or not, but really estimating the inter-class correlation may be more informative than doing a test on the variance, or at least figuring out, is that variance, usually there's variance there. You know, is it 0 or not is usually not interesting. The question is it substantial? Is it non-negligible? Okay, so actually estimating quantity may be more informative than running that test. So here is just a numerical version based on our fitness data. We have 2 programs, so we're going to have 1 degree of freedom for program. We have 5 times, so that we're going to have 4 degrees of freedom for time. And you multiply those, you get 4 degrees of freedom for program by time. And so we can run our tests here. And you notice if we use the mean square for program and divide by mean square residual, we would get an F statistic, an observed value that's very significant. Whereas if you use the subject within program as the denominator, that's not significant. I mean, huge difference here, right? So initially, this is telling us that if you don't account for the repeated measures, you're getting an effect that's very misleading. Now, a lot of times my clients will say, I like this p-value better. I'm gonna go with this one. It's more significant, so it must be right? And there's, I mean, we kind of laugh about that, but I think if you don't know any better, it's like you're picking the p-value that you like, right? The one that gives you the most significant results. So you have to tell your client, no, you can't just pick your favorite p-value. You have to use a method that's the most accurate, okay? And to us, it might seem kind of silly to say that, but you know, it's the same for standard errors. Just because you have a really small standard error from your model doesn't mean it's right. A standard error is something you estimate. You can underestimate it or you can overestimate it. So you want the model that's going to produce the accurate standard error. And similarly with p-values, you can over and underestimate p-values. And so it's important what model you choose and how you specify it should match the data that you have, and the assumptions should be met. Okay, so in terms of that effect, the group or program effect, the one way to think about it is a program effect it's a between subject effect, right? Because when you're comparing programs, you're comparing things that have different subjects in them, in this case. Now, what Jonathan had talked about, the crossover, would be a good way to do this, but that's not how we did it. This is a parallel design, and the subjects stay in the programs that they're in. You know, we could design a crossover, and maybe that would be more, there would be benefits to doing that. But here we're just doing a parallel where subjects are randomized to programs. And so the program effect is a between subject effect. So it makes sense that the denominator mean square for the corresponding F statistic is based on a between subject source of variability. In other words, the subject within well, it's, I don't know if I'd call it a between. It's not a between sort. Between, yeah, I think it's okay. Sorry, I'm going back and forth. You can call it a between subject source of variability, subject within program. I think that's fine. So that makes sense. That use that source of variability in the denominator. But what I want to show you even more mathematically, why we use that for the group effect. And so if we go back to the expected mean squares, if you think about constructing the test, what you're going to do is you're going to have an expected mean square for the numerator and for the denominator. And under the null hypothesis, we're going to have, there are no differences between the effects for that source, right? And in that case, the expected mean square should be the same in the numerator and in the denominator. So let me back up real quick here and go back to this table that we have. And so we have the expected mean squares here. And if, let's start with time. So the expected mean square for that, for time is sigma squared epsilon plus q sub t. What is q sub t? It's just, think of it as a function of the time effects. The greater the value, the more the difference between the tau parameters. So when there are no differences between your time effects, qt is going to be 0. Okay, and it's the same for g and g by t. This q is just a function of the effects for that source, and the bigger the difference between the effects, the bigger q is going to be. And when q is 0, that's saying that those effects are all the same. All of the groups are the same. Then q sub g is going to be the same. If all the effects for time are the same, then q sub t is going to be 0. And that's the important thing. So we're going to look for quantities where if q sub t is 0, then what do we have? We just have sigma squared epsilon. And so that means that this residual that makes sense to use in the mean squared of the denominator, right? Now, if we look at the group effect, we have this quantity here. Now, when there's no differences between the groups or differences between the group effects, what are we left with in that quantity? If the groups are the same, and so the effects for the two groups are equivalent, what are we left with in that quantity that I just circled?
Subject group.
Say again, Jonathan?
The subject group, so the off diagonal, so the sigma squared epsilon plus r sigma b squared.
Yes, yep. So that's what's going to be left, is just these first two pieces, right? So we have to go down the list and see what is the quantity that has that same expected mean square, and it's this one, right? The difference between these two is just that q sub g. And so under the null, if that's 0, then these two quantities are going to be the same. So that tells us that when we develop a test for a group, we're going to use SSG over S minus 1, and we're going to divide by SS S of G divided by N total minus S. That's how we construct our F statistic. Okay. And so that's what I'm mentioning on this, this slide right here. That tells us more specifically why we use that in the denominator for the group test. And we end up with something that's less significant. So that we don't, like, visually, that's the one thing that I said visually, I don't really see a difference between the groups, right? With the average over time. And that matches with results here. What about the other ones, though, that we did see? We saw a time effect. Both groups were increasing, right? So it makes sense that we have this significant result. The program by time, visually we could see something going on there. It's not super strong, but it's borderline significant, 0.08. So sometimes you see it and maybe it'll be significant or close to it. Kind of depends on the data that you have. So in terms of how you run this, if you're to use Proc GLM, you can do the repeated measures ANOVA, and the way that we actually get the correct test is to add this random statement here. And one thing you notice is that in the model statement, we add the fixed effects, which are program, time, and program by time. And we actually add the subjects within program. So even though it's a random effect, we're adding it as a fixed effect in the model. So that's not really correct, but it's the way that we partition the variances and the sources of variability the right way. And then we go back and we can adjust the test to get the right denominator for group. That's the way we do it in Proc GLM. And we get our sources of variability. This talks about, on this slide, how we estimate the variance quantities. If you're to use the repeated measures approach, we actually use method of moments here. So we can take the expected, you think about these quantities. We have our expected mean squares, and we've derived what those should be in terms of the parameters. The method of moments, what you do is you drop the expected value, and then you put hats on the parameters here, and then go back and solve for this for these sigma squared epsilon hat, sigma squared b hat, and we get these in terms of the mean squared quantity. So again, it's nice because you get our variance estimates in terms of the the variability of the data, the sources that we understand, right? So it's kind of nice in that respect. And our numerical estimates turn out to be 21, about 22 for sigma squared epsilon, and then the between subject variance is about 95, 96. Does that make sense based on the data that we saw in the initial figure? I think it was Elise. I think you mentioned you noticed the differences between subject. If a subject started high, they stayed high, and so forth. You mentioned that, right? Well, I think that's reflected in these numbers, is that there's more between subject variability than within subject variability after you account for fixed effects. Okay, so we see that in these numbers. And then if you look at what proportion is due to different sources, we can see that the time effect, so in general, both groups, they're both improving, and the subject variance is about half of the variance of the data. Those two account for 83% of the variance of the data, and those we saw visually. So again, this is just summarizing things that we were able to see visually. Now, if we're to fit this in a mixed model, we're going to see that we actually get a lot of things that are going to be the same if you actually use proc mixed instead of proc GLM. So the similarities between repeated measures ANOVA and the linear mixed model approach, using REML, the estimated variances are exactly the same as using method of moments with repeated measures ANOVA. And the estimates of fixed effects for program time and program by time are exactly the same. The differences between the two, we know that, for the repeated measures ANOVA, we treated subjects within programs as a fixed effect, even though it should be random. It makes more sense, I think, for it to be a random effect. But that's initially how we specified the model. And this is going to lead to some differences in the subject-specific estimates. So you guys probably talked about this in 6612, but the methods that you use for inference for the random effects are actually Bayes methods. And what Bayes methods do is they take a weighted average of subject-specific information and population average information. They take a weighted average of these to get predicted values. And so you can think of what's going to happen is the subject-specific estimates are going to be pulled back towards the overall average. And the weaker the subject data is, the more it's going to be pulled back to the overall average. And relative to the GLM estimates, you're going to see that those shrunk back to the mean a little bit. And we can see that in these graphs. Here, these are predicted values. So we've taken the original data, we fit the model, and we get predicted values. So some of the things we notice in this graph are that it looks smoothed out compared to the actual data. And like I mentioned before, I like to think of it as like running a comb through tangled hair, right? It kind of straightens it out. And that's what we see with the predicted values. But the estimates from the GLM approach, the repeated measures ANOVA approach, are a little bit further out, especially as you get on the top end or the bottom end, compared to the predicted values from the mixed model that use the Bayes methods. Those are in blue. But otherwise, they're pretty close, right? And they reflect the same pattern. Okay, why do we see different patterns for one group compared to the other in our predicted values? What allowed us to get those different estimates for the two different groups as we look over time? Think about the terms in the model that we specify, right? What's the term that allows us to get to see a pattern that's different for one group compared to the other.
It should be the interaction.
Yes, that's exactly it. Who was that? Who was the mystery group? Randy? All right. It's because we added an interaction term that allowed us to do that. Okay. But this shows us with the lower intensity program, it looks pretty linear. Whereas the higher intensity program, it takes a little bit of time for it to see the fruits of it. But by the second, third, fourth week, you see the benefits of the higher intensity program demonstrated there. We're getting close here. I just want to mention a few last things from these slides. There's two types of predicted values for a mixed model. There's one that incorporates the random effects and the other that doesn't. And in SAS, the way that you get the predicted values that incorporate the random effects is to use the out-P statement. And the one that doesn't incorporate the random effects is out-PM. So remember, there's two types of predicted values. There's one that incorporates the random effects and the one that doesn't. And here's the code that we can write in SAS, the exact proc mix code that you can use to carry out this analysis. And here I'm showing, the random effect estimates that we can obtain if we add the solution option in the random statement. That will actually give you the random effect deviations for each subject, and then actually a t-test to show you whether that difference is significant or not. And you see these estimates, do those look familiar? Those are the exact same that we got from the method of moments approach for repeated measures of ANOVA. Exactly the same. But in general, what I'm mentioning here is that, inference in a mixed model, we don't generally we don't create an ANOVA table. It's just that with this specific type of model, they turn out to be the same. If you're an R user, I did actually put in some R code here and the packages that you need. LME4, which is a random effects modeling approach. And here that's what we're using. We just put in a random intercept. The M means, you guys familiar with that package? That allows us to get the expected marginal means, and then a few other packages that we need. So you'll be able to see that the results we get using R is the same. And this is just a mention of the degrees of freedom, which I'll spend more time talking about next week. Different approaches to estimate degrees of freedom. But finally, on the last slide, here I'm just showing the random effect estimates. So the thin lines are these, and so I'll call those the predicted values, and the thick lines are these, right? And they could both be of interest. These are going to be the biggest, probably the main thing that we get. We see the overall average differences between the two programs. And again, a straight line, an increase, importantly, for the lower intensity program, and then an initial fairly flatness, and then a more increase for the higher intensity program. So those are probably the most important thing, but this also reflects the fact that there's more variability between subjects in the higher intensity program than in the lower intensity program. So it kind of mimics the data, but it just, again, it straightens out the values a little bit. All right, so thanks for, we actually got through a slide, so I won't have to finish up a slide set next time, and we can dive right in Wednesday on the next slide set, the next review stuff. I will post it. I haven't figured out, I haven't decided yet, homework 2, whether to make it shorter and do next Monday or longer and do in 2 weeks. Do you guys have any preference? Would you rather have shorter, more frequent homeworks or longer homeworks that you hopefully don't wait till 2 days before to start?
Shorter.
Shorter? One vote for shorter. Any other votes for shorter? Any votes for longer? If you don't say anything, then longer. So one for shorter, one for longer, and the rest, or you're just so flexible. You can do.
I'll vote shorter.
Okay. Okay. Let's do it this way. Shorter. If you want it shorter, raise your hand. If you want it longer, still the same. I'll have to think about it because it's roughly split down the middle. So I'll think about it. Either way, I'll post that like today or tomorrow. So thanks everybody for hanging tight. I'm around. Hopefully you're pretty much done with the homework. But we'll talk Wednesday. So thank you. Bye.